Nusselt's number and Schmidt number. Similarly, you will be doing, and that was around a particle. Now you will be doing around a bubble. So that's the main difference. And it shouldn't take you too long because it's very similar to what we have done in the class. Then just so that you can all put in your notes, the final exam is on the 11th of December. It's in the same room. So we'll have it here. I will obviously send out an announcement as well. It'll be for 2 hours and we'll post a practice exam in advance. So it's slightly longer than your midterms, like 2 hours instead of 1.5 hours. But it'll have two sort of long problems instead of one, but neither of them will be as long as the one that you've been doing in exams. And then there'll be some conceptual questions, and you will see the practice exam kind of takes care of that as well. Any questions for the exam and the homework? And yes, only the material that we have covered after exam 2 would be the finals. So you don't have to go back to part 1 and part 2 of the course. Okay, so it will be focus on part 2. Any questions for the exam and or the homework? All right, we'll have office hours today. Then I'll have office hours on Wednesday, and then Felipe will have office hours on Friday. And then, next week we will obviously have office hours as well for the homework. All right. And then finally, I just wanted to kind of quickly, briefly recap what we have been discussing about after exam 2. The first thing that we discussed was momentum boundary layers and how basically like we discussed about the drag forces. So we calculated, the boundary layer thickness, momentum boundary layer thickness, calculated drag coefficient, and so on. We discussed about bluff bodies, different shaped bodies. That was chapter 9. Then we discussed forced convection heat mass transfer, where convection impacts heat and mass transfer, and not that heat and mass transfer does not impact convection. So you first find a velocity profile, and then we discussed 2 types of problem: confined flow. So confined flow was stored in a channel, like you can imagine like a pipe with some sort of temperature boundary layer forming, or unconfined flow, where we had forced convection heat and mass transfer around a sphere. All right, so this is basically the 3 topics that we have already covered. Chapter 9 was the momentum boundary layer, chapter 10 was the confined flow, and then chapter 11 was the unconfined flow. Okay, and now there are chapter 12 and 13 in the book, which are not part of the course, but I just want to kind of briefly mention them. One of the chapter basically focuses on multi-component diffusion. So let's say if in your research, especially in catalysis research, for instance, there can be multiple components of gaseous species, or in electrochemical research, there could be multiple components, and there essentially there will be the chapter actually can be helpful. So just to keep in mind, there is also some discussion on turbulent flows, in case you end up working in a system that has that, which you don't cover in the course. But basically we'll skip over chapter 12 and 13, 12, 13, and 14, and the last chapter we'll discuss is chapter 15, just transport in electrolyte solutions. Okay, so for the rest remaining 4 lectures, we will discuss chapter 15, and we'll go to learn how the transport phenomena changes if instead of neutral species, now we have charged species, like we have an electrolyte. Okay, so any questions again? Anything about the layout, the remainder part of the course? Anything that's confusing you want to clarify? All good. Okay. So let's quickly motivate this. We have been discussing about motivation of boundary layers for automobile design and other sort of drag forces. Then we discussed how heating pipe, heat exchangers. But when you think of electrolyte transport, it's actually, I would say, one of the more more modern applications. For instance, one of the key applications is electrochemical devices. So you all know what lithium-ion batteries, solid-state electrolytes. So basically there are also desalination devices. Now there is electrochemical carbon capture. So there's a lot of emphasis on using electrochemistry to kind of drive these processes, and all of them involve electrolytes. So you need an electrolyte. Sometimes it can be an ionic liquid, sometimes it can be just a organic electrolyte or an aqueous electrolyte. In all these cases, there is an electrolyte transport. Okay, and it is a very active area of research, and there is interest. So what you see here is something like an electrochemical capacitor, which is essentially like a battery, but it does not reuse reactions. It just physically attracts the ion and puts them inside these pores, and that can give you high power density, and basically can be used in sort of complementing batteries in electrical vehicles. It can sometimes be used to match supply and demand on electric grids. And again, a very active area of research. There's also flow batteries, by the way, which are also becoming very, have again gone again popularity, where you have fluid mechanics plus electrochemical transport. So there's again a combination of many of the things we have been discussing in the class. All right. So the other topic is, this is sort of a more energy storage sustainability side. The other thing is that many of you might be interested in diagnostics or microfluidic devices, or using lab on a chip applications. And there's a very cool area. It's called electrokinetic phenomena. And to give you an idea, this is a video you will see here. What you see are essentially parking spots. So if you read this paper, they have basically created these parking spots where they take DNA and put them on spots. So I'll first show you how they park them using flow. So let's see. So they have basically taken these long DNA molecules and kind of put them on these spots, kind of park them on a spot, and then they will turn on the electric field. You'll see, and it will take a few seconds, then they will turn on the electric field, and what you will see is it stretches it out. Okay, so it stretches it out and kind of they can kind of control this sort of stretching process. Okay, and it's a very kind of like a nanofluidic, microfluidic. This is a very interesting application of using electrokinetic phenomena. So why do we read it in transport phenomena? It's because think of, so I mean, that's a very simplistic picture on top. That's a charged particle, but it could be a charged polymer, it could be a charged macromolecule like a DNA, could have an odd shape, but it needs an electrolyte in the background. So to kind of have this process, you add an electrolyte and then you apply an electric field. And these electrolytes essentially respond to this sort of charged molecule. So they transport closer to that because of diffusion and something else that we'll discuss today called electromigration. And combination of that kind of yields this rich phenomena, which is very, very useful. And if you know, obviously, electrophoresis is actually one of the key processes which has shaped a lot of DNA sizing. Gel electrophoresis is a process where you essentially separate DNA by sizes, and that is all based on electrokinetic phenomena and electrolyte transfer. Finally, I'll also mention something that I used to work during my postdoc, and these are essentially fluorescent labeled charged particles that are going in a dead end. So they wouldn't be able to go into deep dead end. So there is like imagine these are just like sort of kind of channels which have an end. So you shouldn't have anything going inside, flowing inside. And they're only migrating because, and their diffusion is very slow. So they will never really go inside because of diffusion, but this is called diffusiophoresis. So essentially you create a concentration gradient of an electrolyte, and that pushes these particles inside. And it's again a very active area of research. My group was just at a conference where you probably had like 10 talks on diffusiophoresis. Because again, very, very sort of a non-invasive electric field, you're still applying something. Here you don't even apply a field, it's just a concentration gradient driving the motion of the particles. So diffusiophoresis is again also an interesting process. This is also an electrokinetic phenomena, which is used to sort of drive the motion of the particle. Okay. At the same time, I just want to quickly mention something. This is just by chance, it wasn't planned like this. Is tomorrow the department seminar is exactly on the same topic. So Professor Ashwin, his topic is on nonlinear electrophoresis. So this will be very relevant to something what we discuss in the course. Obviously, the talk will be on more advanced topics, but you will be able to kind of get exposure to more of the modern research in this area. So I highly encourage you to attend this. As you will see, we will discuss some of the same equations, same ideas in the class next week. So it'll be kind of a nice sort of sort of a nice coincidence. Okay, so please do attend the talk. He's an expert in electrokinetics. Finally, just the last part, I want to mention something that my group has been doing. And this is actually Felipe's work from his PhD. So what you're seeing here essentially is an electrolyte transport in porous material. So I'll just quickly show you something here. So this, as you saw, this is kind of like a porous material. As you can imagine, there can be connections here, sort of bifurcations, connections, loops, and so on. And for a long time, the work has basically focused on single pore analysis. And what Felipe's PhD is focusing is on how to kind of extend that to a random network of pores. So Felipe has kind of developed a lot of theoretical analysis. And what this result is showing here is that for the same pore size distribution. So if you hear about pore size distribution, the connectivity matters. So if you have something which is decreasing in pore size or randomly distributed or increasing, you can have a very different current profile. And again, all of this is electrolyte transport. So this is obviously a more advanced topic, but I just kind of just wanted to briefly mention this, and we'll talk about this in the next lecture on how to think about this sort of time-dependent process and how does it relate to energy storage. Okay, hopefully this is a good enough motivation. Any questions on any of these things about applications or any of that? All right. So let's go and start thinking about how to think about transport in this processes from a fundamental perspective. All right. So let's start. So this is chapter 15, transport in electrolyte solutions. All right. So basically, I just want to kind of briefly remind you of something that we have discussed earlier, and that is governing equation for species transport. Okay, so now we are going back, and we also discussed this in the concentration and momentum boundary layer and temperature boundary layer, but species equations are del Ci by del T, and I will use it like this for now. All right, okay. So remember that this Ni was the flux of ith species. This was the volumetric reaction. And this was the accumulation term, right? So when we derived this in part 1 of the course, we discussed in minus out plus generated is equal to accumulated. We added fluxes and so on, and we derived this equation. In the first part of the course, we said we'll forget convection and only think about diffusion. And in the second part of the course, we derived what the convection would look like in terms of velocity profiles. And the third part, we're saying, well, you can have both conduction or both diffusion and convection. That's why we're deriving things like Nusselt's number, Sherwood number, and so on, right? So this flux, essentially Ni, had two parts to it. First part was velocity times Ci minus di gradient of Ci. Okay, flux had two parts. This was the convective part. Actually, it's more commonly written as Ci times velocity, just to be clear. This is convection, and then this is diffusion. Okay, and so the whole course really, first part was what if I remove the convection part? Yes, good. Oh, sorry. Thank you. Yeah, thank you. Yeah, the connection is a plus sign. So the whole course really was about how to kind of solve the diffusion problem first, right? Ignoring convection. Then we solve velocity profile separately from Navier-Stokes equation, and then we combine the process in the when you have forced convection, heat, and mass transfer. So just to emphasize, this was the whole description. So this is how what we were operating under the assumption till now. But now we have an electrolyte. So what should be an electrolyte? So if you're thinking of an electrolyte, just think of something like you have a beaker or a cup in your home, and you put water and you put common salt. Okay, so common salt in water. As you know, common salt is not going to stay like itself. It will dissociate into ions, right? It'll have Na plus and Cl minus ions. So this is what we are thinking about. So remember, but when we kept thinking about this, all of these reactions was for pseudo binary. Just to recap, this was for pseudo binary constant rho systems, right? So we discussed how density is constant. We kept saying liquid. Think about a liquid phase. In a liquid phase, you said you are dissolving a gas, something like that. So, dissolved carbon dioxide in water, dissolved some other species in water. But now I'm saying instead of dissolving something like a gas, I am essentially now dissolving an electrolyte, okay, an ion, a kind of a compound which dissociates into two ions. For the purpose of this course, we'll only be thinking of completely dissociated ions. So there is obviously a whole chemistry involved where you may have partial dissociation. So what is an example of partial dissociation? Acids, right? Yeah, so you can have weak acids, which may not dissolve completely, and we'll have partial dissociation, but we'll think of something like strong electrolytes, which should completely dissociate. Okay, so that's just, let's keep it simple. So what do you think is different about these things? What do you think? Now let's have, imagine you have a sodium ion and a chloride ion. It's sitting in a beaker. How can I move them without disturbing them, without adding any concentration gradient or any velocity? Can I move them? Can I have a transport through them? Electric field, right? Because they are charged now. So essentially, and for that, you don't need to have any velocity or any concentration gradient. You need to have a potential gradient or an electric field. Okay, so that's essentially what we will focus on. So the third type of transport mechanism is called, and we'll go through the terms slowly. So don't worry about it. Minus di zi cif by RT gradient of phi. Okay, and this term is known as electromigration. Due to electric fields. All right. So first, I want to again emphasize that note that our governing equation, basic equation, was derived earlier. It's not something out of nowhere. All we are doing is adding a new kind of flux, which can happen because of a potential gradient. So what are these different symbols? So some of them you have already seen, but let's just recap them anyways. Di is diffusivity of the ith ion. Or or if it's new, you can also call it neutral species. In that case, we will discuss what will happen. Zi is the valence of the ith ion. Ci is the concentration of the ith ion. Faraday's constant. F. R is the Boltzmann constant. T is the temperature in Kelvin. And phi is the electric. Phi is the electric potential. Okay. So hopefully you can see it here. Yeah. Both. Yeah. So this is essentially all the different symbols. Di, Zi, Ci is the concentration. So Di is the diffusivity. I had seen it before, but just to recap, Ci is the concentration. Then we have added this valence of the ith ion. Then the Boltzmann constant, Faraday's constant, temperature in Kelvin, and electric potential. Okay. So note that you can actually derive this. So what I have done, I've skipped over some of this step. So can anybody, maybe this is something you have read in thermodynamics. How do you define a flux? What is the origin of a flux? A gradient of what? Chemical potential, right? So we basically, I presume you might have discussed this in thermodynamics, but if not, a gradient of a chemical potential drives a flux. So if it's purely entropic, you get a usual diffusive flux. Now what happens is when you have an ion, your chemical potential also has an electrical part of it, because you also have some free energy stored in terms of electric portion. So essentially use those thermodynamic quantities to derive it. So it's not out of nowhere. We just haven't discussed it, for simplicity. But so that term can be derived, like diffusion can be derived. Similarly, you can also derive the electromigration from thermodynamics. We'll just skip over that for the purposes of for the course. Okay. Now, what is this valence of the ith ion? So valence is essentially the unit charge carried by the ion. So unit charge carried by the ion. So for instance, for Na plus, this Z would be +1. For calcium, it will be +2. For chloride, it will be -1. Okay. So that is essentially the idea. And what will happen? What will happen for a charge neutral species? What should be the valence? 0, right? So that's why that term goes away. So it only occurs for something that's charged. +1, +2, -1, and so on. So that's the valence. Then concentration is there. So how should can anybody kind of just sort of physically think? Why do you think this depends on? It's kind of proportional to Zi times Ci. Okay, I just want to kind of get some of the, because we haven't derived it. I want to physically motivate this. Why do you think it depends on Zi times Ci? Charge density, absolutely right. So concentration is is essentially the number of molecules per unit volume. Now I'm multiplying it by the charge carried by it. So that's why you get something like charge density. And why is the flux proportional to charge density? Because remember, an electric field times the charge is the force, right? That is the force, and we're trying to find something related to transport. So that is charge density, and that's why the Faraday's constant also comes. So let's also write down the units of this. Meter square per second, we have discussed this. Let's use a different color. Meter square per second. Zi is dimensionless. Ci is mole per meter cube. And what is this charge? Charge is coulomb per mole. That is the charge carried by one mole of electrons. Okay, so it's, I think it's if I'm not wrong, I believe the number is 96,500 coulomb per mole. Okay, that's the Faraday's constant. So, and then R is joule per mole Kelvin. Joule per mole Kelvin. T is temperature, is Kelvin, and phi is potential, which is volts. Okay, volts. So it's actually it will remind you some of the things you might have done in your undergrad physics. If you kind of multiply all of this, you should be able to get the units of fluxes. Okay, it's instructive to go through that, and remember that charge times voltage is energy. Okay, so that's kind of charge times voltage is energy. So you get a joule out of that, and so you'll be able to cancel out the terms. But do try it if you kind of if you would. It's kind of instructive to try that. Okay, all right, and get the units to be mole per meters per second. So this is the first thing. So that's why we have a Faraday's constant, because we are dealing with molar units. Then Boltzmann constant, and that comes from the thermodynamics part. One thing to notice here is that this term here, let's look at this term here, F by RT is sometimes known as so let's do it, RT by F. So RT by F, so this is joule per mole Kelvin, by coulomb. So joule per mole Kelvin times Kelvin, coulomb per mole. Okay, so this gets cancelled, mole gets cancelled, is joules per coulomb. Okay, and what is joules per coulomb? Volts, right? Like energy per unit charge is volts. So this has the units of volts, and sometimes it's known as thermal potential. Okay, thermal potential. Why is this called thermal potential? Because essentially this is the electric potential created by Brownian motion of these ions, RT by F. Okay, and at room temperature, this is essentially 25 millivolts at room temperature. Okay. So just to give you an idea. So that's essentially what basically you are doing is you're kind of comparing the potential in your system. So look at the top right. That's the grad phi. So phi divided by RT by F. So in a way, you're comparing the motion due to as compared to the Brownian motion due to the electromigration. So that's how the RT by F in a sense comes out. All right. Now a question for all of you. So we have discussed it's proportional to Zi times Ci because it is the electric field is electric force is proportional to charge, and in this case with charge density. What if my potential is constant? Should we expect something to have a transport? Look at the equation. Do you think if my potential is constant, will I get a flux, electromagnetic flux? So the gradient will be 0, right? So it will not happen. So this is a very common mistake. Students think if there is an electric potential, you will have a flux. It is not the electric potential that will drive a flux. It is the gradient of electric potential that will drive a flux. Potential as such is arbitrary, as you might remember. You can set it to be 0 anywhere, or a reference value. So that's why it doesn't matter. It's the gradient of potential or electric field. Okay. Similarly, a concentration does not drive the flux. It's the gradient of the concentration. Similarly, the gradient of the potential that drives the flux. Just remember that. Okay. All right. Any questions on this electromagnetic flux? Yes. Physically, what's the thermal potential? So let me try to make a sort of a, so the idea, think of it like this: if my electric field is if I take this RT by F inside the gradient, right? In a way, the electric field has to be rather the potential change for delta phi. So let's put it like this. Physics.
Like the potential required to overcome the
thermal potential. Absolutely. So, and that is how you will derive it. So when you derive it from, when you derive the flux, that's the way you derive it. So it's essentially, think of it like this: if delta phi, I'm not talking about gradient of phi, delta phi, change in the potential is much smaller than the 25 millivolts, you can just not expect anything to happen because the Brownian motion will overtake and that term will just go away. So you need strong electric fields. I mean, 25 millivolts is not really that large, but moderate electric fields to kind of drive any motion. So that's essentially the idea, is that it has to be comparable to the Brownian motion, and that's why you have the RT. Absolutely. Anything else here? So at very high temperatures, as you can imagine, this will essentially not be feasible because your Brownian motion will be so high, then your moderate electric field will just not be important. The Brownian motion will take over. All right. So we have this. Now, what's the problem? I have the flux. Should I be just able to solve this? Can I just solve this equation now? I have, let's say, the velocity, and can I just solve the system? Now I have added a new flux. Why and why not? Anybody wants to volunteer? Why do you think I can or cannot solve this? Yes, we have now also added a new variable, which is potential. So I need another equation now, right? So I need another equation. Now that I've added a new variable, so we need another equation. So in our governing equations, we have modified a little bit, but we have added a new variable called potential. So we have added a new variable phi. So we need another equation to close out the system of equations. Okay, so we have added a new variable phi. So we need another equation to close out the set of equation. Previously, in one of the previous classes, I had actually derived the equation, but I will just skip over that and give you the equation because I think it's still instructive. And it's not new. This is something you have actually seen in your freshman physics class. That is the Gauss's law. Okay. So we started the Gauss's law, do divergence theorem, and try to come to a differential form. I will just write it and explain how that is the equation. So the final equation is basically known as the Poisson's equation, or it's the Gauss's law. Poisson's equation, or the Gauss's law, and it's called minus epsilon del square phi is equal to rho e, and I will discuss what this rho e is. Equal to zi cif. Okay. So here epsilon is the electrical permittivity. Electrical permittivity. Units are farad per meter. Farad is not the Faraday's constant, just remember this. Farad per meter, this is the units of epsilon, and it's the units also of capacitance. We'll come to all of these things. We just want to clarify that don't get confused with this F. This is just for the units. Unfortunately, there is no other symbol for this, so the book uses this, so I'm using this as well. Then rho E is charge density. Charge density. Okay. Charge density, and basically this is, note this, the units of this is dimensionless times mole per meter cube times coulomb per meter cube. So this becomes coulomb per mole, sorry, coulomb per mole. And so the unit becomes coulomb per meter cube. So for the units give you some feeling that it's basically the right hand side is charge density, because the units are coulomb per meter cube. Coulomb is a unit of a charge, and then you have a charge per meter cube. Okay. All right, so this is the equation. How do you derive it? So you might remember that this is the charge stored inside two different, E dot dA is equal to Q. I don't know if you remember that, but basically you kind of find the flux of the electric field. So if you take a kind of like divergence theorem and do a differential element, you get this equation. Don't worry about the derivation, but just to show you, it is relating potential to concentration, right? So if we add this equation to a set of equation, we get a consistent set of equations. Right? This is relating potentials to concentration. So why? And this equation is very notorious. Why do you think that would be the case? This equation is really it's very difficult to deal with. Do you have a sense of why that might be the case? Sorry? Non? It's non-homogeneous. So good track. So very good track. So think of it like this: is that I have a gradient of phi here, right? And I have a concentration. The sum of my concentration is related to second derivative of the potential. So it becomes a highly coupled equation, which is highly nonlinear. And the conference I mentioned to you, we went to recently. There was a talk on how this is as difficult as solvent turbulent problems. Because this coupling, this is really difficult coupling. It becomes a multi-length scale problem, and this actually resembles very much like the whole structure of the equation kind of becomes very complex like turbulence. So that's why we will not solve it in the full detail. We kind of simplify the equations and solve it in only simplified circumstances. But I just wanted to show you mathematically why this is nonlinear. Now the right hand side is very instructive. Okay, so I think somebody had mentioned Zi times Ci, right? So Zi times Ci times farad is essentially charge of one of the species per unit volume. And now I'm summing all of that to get the total charge at that location per unit volume. And so that's your summation there, okay? So that's where Zi times Ci times F is basically the right hand. Okay. Any questions here? So I just want to first really want to make sure this is very clear. So let's close the system of equation. So the system of equation is the system of equation is, this is called the Poisson-Nernst-Planck equations. And what you get is del C by del T plus V dot del Ci is equal to di del square Ci plus di Ci AZIF by RT. Okay, so Ci grad phi. So this is the new part. This is the new part. The first part you had already seen. This is the electromigration part. And I already substituted the value of Ni and just kind of rearranged everything to make it look similar to what we had seen before. And then I add the epsilon del square phi is equal to summation Zi Cif. Okay. So these are known as the Poisson-Nussbaum equations, and these are the governing equations for electrolyte transfer. Okay. Yes. Yes. Yeah, great question. So what the question is, would this term be zero for a sodium chloride, because the charge is equal and opposite and the concentration is the same, right? And the answer is yes, but only if it is in bulk. If I put, let's say, a charge in the system, a surface in the system, positively charged, all the chloride ions will get attracted to it, in the potassium ion will get rejected. So this is true, and this is what we will discuss as the first approximation is when the system is in bulk, then there is no net charge because there is no reason to collect charge. It's just, let's say, it becomes neutral, and that's called the condition of electron neutrality. But a great question. This term is not always going to be zero. Remember, it can be non-zero, and that is what we'll discuss on Wednesday. And that's when you have a charge surface near it, you can have naturally net charge, right, to balance the charge on the surface. So this term is not always going to be zero, but it is going to be zero in bulk. When there is no charge, why should an electrolyte carry any net charge? There is no reason for it to have charge. So we'll discuss that in a bit. Okay. So any other questions here? All right. Are we done now, or do you think we are still missing something? So we have the set of governing equations. We need boundary conditions. Okay. So the first step is the governing equations are set, but we need the boundary conditions. Governing equations, and you need the boundary conditions. So I'll keep it simple. Remember that you had in concentration, constant value, constant flux, and then you had a mixed condition or the interfacial balance. Okay, remember that this is what we discussed in part 1, constant value, constant flux, interfacial balance. Similarly, we also have for phi constant value, constant flux, or a mixed condition. We'll discuss them separately when we go to the exact problems. Okay, we'll not discuss them right now, but I just want to mention that very similar, like concentration, you can have constant value, constant flux, or a mix. Okay, so constant flux is what you'll see in your homework. We'll discuss it in next class. And constant value is simply, potential goes to 0 or potential to the value. Mixed condition is something we will not see. There will be one homework problem which has a little bit of that flavor. I will not discuss in detail, and I will when you get to the homework problem, we can discuss it. Okay. All right. So just to reiterate, we saw the Poisson-Nussbaum equations. The one thing that I have not discussed is velocity. Okay. So the velocity, I have just skipped over it. So it is assumed here that the velocity is known. And the first part today and Wednesday, we will discuss the cases where the velocity is simply 0. And on Monday, I will show you how even your Navier-Stokes equation change when you have an electrolyte. Okay. And so you have to write a new set of equations, and then even the velocity might change. Okay. So we'll not discuss that for today and Wednesday, but I just want to emphasize that velocity here, it's implicitly assumed that you know the velocity, but the equations that from where the velocities come can also change because of the electric force, because there is a new force in the system now. So you have to take care of that, but we'll come to that on next Monday. I just want to emphasize. So these are our governing equations, and these are our boundary conditions. And with that, let's take a 5-minute break. And when we come back, we'll discuss the simplest cases of solving this problem, where something really interesting emerges. We'll start at 12:50.
Oh, yeah. Yeah, I think that's. I don't know what that is, but I put on the seat, so. I think my thought, I did lunch, but. Not yet. Kind of good price on. Yeah. Yeah. You go. Yeah. Yeah. Super relevant.
Why is it always?
I don't know. I've actually been like that for 2 years. I have no idea. Like I don't know. Like when I look at it here,
Yeah.
it says 9:41. I don't know. My best guess is that this is Tuesday, Jan 9.
Yeah.
My best guess is the when I purchased the good notes for first time. That's the time it goes.
Okay. So when you go out of the app.
Yeah, I've been using it,
But it's in the app, it only shows that.
yeah, it's like it's just I have never understood about it because that's the big issue.
Yeah.
She graduated college. Oh, they have to do it. Like,
All right, let's get started. So for the remainder of the lecture today, we'll discuss a very simple topic, which was alluded to as per the Q&A, and that's bulk electrolyte transport. So we'll discuss bulk electrolyte transport. Okay. Bulk electrolyte transport. And that basically means that rho E is equal to 0. So this is what the question was just asked, was about that if I have sodium and chloride ions, why should I have any charge. I mean, it's ZiCiF. Remember that this is ZiCiF, and the point is that if the concentration of NaCl is C, then the concentration of concentration of the chloride ion is the same as the sodium ion. The charges are opposite. So when I sum them, essentially I should get a ZiCiF. We should get it to be 0. Okay, that's the idea. Okay. Now, if that is the case, that I have net charge to be sort of 0, and I also have velocity to be 0. So assume, this is assumption. Okay. Now I can write essentially the equations. So let's revisit our equations. Poisson Nernst Planck equation. And let's imagine, remember, this is how we have developed the entire course. We start with assumptions, and the simplest thing is 1D, right? We say 1D problem. To simplify the life, we say 1D. Okay, so let's assume a 1D system. So we have del C I by del T plus V dot del Ci is equal to di grad square Zi plus di Zi Ci. So di Zi F by RT. And then del dot Ci grad phi. And then the second equation is the minus epsilon del square phi is equal to rho E. These are our equations. These are our Poisson-Planck equations. I've just listed them down again. And now let's try to drop terms one by one. Okay, so we know rho E is equal to 0. So this goes away. By the way, we should also assume, for simplicity, let's assume we only have two ions. Two ions, C plus, C minus. Okay, and then their diffusivities are D plus, D minus, and valences are Z plus, Z minus. Let's just assume that we have this simple system. Keeps things easy, and we get this to be 0. So this goes away, and then the velocity term goes, right? So we get simply velocity 0, that 0, and then I have two ions, so I can technically write down the equations in these two ions, right? So I get del C plus by del T, and note that I will now move from 3D to 1D. Then I'll say D plus del square C by plus by del X square plus D plus Z plus by F by RT del by del X of C plus del phi by del X. Similarly, I can write del C minus by del T is equal to D minus del square C minus by del X square plus D minus Z minus F by RT del by del X of C minus del phi by del X. Okay. So I hope this is not confusing or anything. So you have the usual, if I remove this part, if I remove these terms, this becomes an unsteady diffusion problem, right? We have discussed this in part 1 of the class. Unsteady diffusion, where we discuss FFT, similarity transform, and so on in these two terms. But we have just now added this. And by the way, we are assuming there is no reaction in the entire process till now, which is generally okay to assume. So just wanted to clarify that. So this is all of our equations. And the third equation is epsilon, or simply I can say del square phi by del X square equal to 0. So these are the three equations I have. And what can I do? I have any other equation that I'm kind of sort of not stating it here? Sorry. Continuity. So the good session, but know that the velocity is 0. So the del dot V velocity is 0 is automatically satisfied. So I don't have to kind of use it. But implicit in this is that Zi Ci Z plus C plus Z minus C minus is equal to 0, right? So I've already used, we also have this equation, or Z plus C plus Z minus C minus is equal to 0. Okay, so I cannot use both, right? Either I can use this or I can use this. Right? I mean, I can't have more equations. Any questions here before I proceed further? So it's an unsteady transport. Instead of having just diffusion, we also have electromigration, but with an additional condition that we have electroneutrality. Now, I have a question for you. So we have this equation, which is sort of not really helpful because it's not helping me couple this equation, right? It's just a separate equation, just there. I can't really do much with it. I want to, let's say, and I'm telling you this, I want to exploit this equation, z plus z minus equal to 0, using the first two equations. Does anybody have a suggestion how I can exploit this z plus z minus c minus, and specifically the goal is to eliminate phi from the equation, right? Because if I eliminate phi, let's say I forget this equation, I'm using this equation, and I eliminate phi, then I'll simply get two equations in c plus and c minus, which is great. Then I don't have to worry about any other equation. So any thoughts on how I can eliminate, how I can use z plus z minus c minus and eliminate the other equations? Eliminate phi.
You do the product rule and then you would have a second derivative phi.
So yeah, good observation. So I hope everybody can follow on what Tim said, is that you see here z plus c plus and z minus c minus, right? And I can obviously take the z plus inside the derivative. If I add them, I will get a z plus c plus z minus c minus. But there is a problem here. What's that? That there is also d plus and d minus. Right? D plus and d minus are not necessarily going to be the same, right? They can be different. So what should we do? Any thoughts? Just divide by d plus and d minus, right? And then add them. Because if you divide by d plus and d minus both equations, this was d plus and this was d minus, then when you add them, this term will just drop out. Okay, so I hope you can see that. So let's divide this by, multiply this by, so divide by d plus, divide by d minus. So I get del c plus by 1 by d plus by del t is equal to del square c plus by del x square plus f by rt, and I'm just writing it like this so that you can see it. Z plus c plus del phi by del x. Then I have 1 by d minus del c minus by del t is equal to del square c negative by del x square plus f by rt del by del x of z minus c minus del phi by del x. Okay. First, I want to everybody to be comfortable with this. Any questions here? First, this step. Any questions? All good. I just divide the equation by d plus. I've divided the equation by d minus, and I've just left them like that. Okay. Does everybody agree with this? Any confusion or questions here? All good? Okay. So now what should I do? Add them, right? Just add them. So if I add them, why am I doing that? Because I know z plus c plus z minus c minus is equal to 0. So when I add them, I get 1 by d plus del c plus by del t plus 1 by d minus del c negative by del t is equal to del square c plus by del x square plus del square c minus by del x square plus f by rt del by del x of z plus c plus z minus c minus del phi by del x, and this term is 0, or I simply get 1 by d plus del c plus by del t plus 1 by d minus del c negative by del t equal to del square c plus by del x square. All right, so I've just added them. and I get this equation. So I've eliminated 5. So first thing is I've eliminated 5. That's good. Okay. So what? I've eliminated 5. Do you think this is equation is helpful, or do you think there is something else we can do here? So the first, and let's recap. We had these equations. We used the electron neutrality to get rid of the phi term. So I have now an equation in terms of C plus C minus. Great. I don't have phi, which is good. But what else can I do? So do we know a relationship between C plus and C minus? Yes, we know it's Z plus C plus is equal to Z minus C minus. So you know Z plus C plus Z minus C minus is equal to 0, or C minus is equal to minus Z plus C plus by Z minus, right? So I can substitute this back here. Okay. And I'll just get an equation in C plus, right? If I just also now write C minus in terms of C plus, then I'll just get an equation in terms of C plus, and that equation I will let you do this at home, but it's very, very nice. It's just really beautiful that you get this term out. You get del C plus by del T is equal to Z plus minus Z minus D plus D minus by D plus Z plus minus D minus Z minus del square C plus by del X square. So this is what you get out. Or another way to write this is del C plus by del T is equal to D effective del square C plus by del X square, where D effective is equal to Z plus Z minus D plus D minus D plus Z plus. So there's a plus here, not a minus. D plus Z plus minus D minus Z minus. Okay. Isn't it amazing? So you get an unsteady diffusion equation for C plus, and you know how to solve steady diffusion equations. So in the bulk transport, we have essentially first eliminated phi using electron neutrality. Then we again use electron neutrality to get an equation in terms of C plus. And the fact is, the difference is now my diffusivity for the plus ion is not just its own diffusivity. It's actually the diffusivity of the plus ion and the negative ion combined, and also weighted by their valences. And this is an equation that you get, and this is called ambipolar diffusivity. So if you read any of the text on electrolyte transport, this is very commonly used, ambipolar diffusivity. It's a beautiful result. It's basically saying that don't worry, still an electrolyte transport is like a diffusive transport, but the diffusion coefficient is no longer its own diffusion coefficient. The two are sort of interacting, and that's why you're getting this. Any questions here of how we got here? So first we eliminated phi by using electron neutrality. Then we eliminated C plus C minus and to get this. Okay. Any questions? All right, so we got this answer. Let's try to physically understand this more. So we got this answer, and now let's take this question here. What do you think is the effective ambipolar diffusivity for C minus? Okay, so we have derived the result for C plus, but we have to set anything for C minus. What do you think is the effective ambipolar diffusivity for C minus? I would encourage you to look at your equations again, look at all the results again, and then select an answer. And we'll discuss this several times. right, maybe let's give another 15 seconds. So take your time. It's not rush. Just really want to. This is a very important aspect of electrolyte transport. What do you think is the effective ambipolar diffusivity for C negative? All right. So then maybe another 5 seconds in case anybody else wants to get their answer in. Then we'll close the poll. All right. So let's close the poll. And let's look at the results. So it's split A, B, C, D. It's all the options have the responses. The correct answer is A. It is defective, and this is one of the most confusing aspects is why A mathematically, and then we'll discuss physically. Okay, so mathematically, as you can see here, I can multiply both sides by minus Z plus by Z minus del C plus by del T. Right, and why am I doing that? Because I can see this result here. C negative is minus Z plus C minus. Okay, so look at the top right. We have a linear relationship between C plus and C minus. And so essentially this can then become essentially del square C negative by del T equal to T effective. It's just linear. So you can just go between C plus and C minus anytime. And so very commonly, this is not written like separately. They write C plus minus, C plus minus. Both the ions have the same diffusivity. Effective diffusivity. Can somebody suggest why? Why am I having the same diffusivity of both the ions? Any thoughts?
Well, the charge is still behave the same way.
So that's an interesting comment. So that is true. So what Tim is saying is they should be symmetric. That's a fair point, but the way to think about this is sort of more about the electroneutrality assumption, right? Let's say I have two ions. Okay, so let's say I have two ions, and one of them wants to outrun the other one, has a large diffusivity. But if I allow it to happen, then what will happen? Then I'll have a charge separation now, and I'll develop a net charge, but I'm not allowed to develop a net charge. So I will be able to kind of have to keep the diffusivities to do the same. Okay, so physically, I cannot have one ion outrun the other one. And so they both behave through an effective diffusivity. They cannot have, and one cannot have a larger diffusivity than the other. And so how am I doing this? How can I diffusivity is diffusivity. So how do you think is this sort of able to happen? How am I able to kind of keep the diffusivities the same? Math is giving us this, but physically, let's say this ion is 10 times faster than the other. How is it that the effective diffusivity is going to be the same? So let's try to think about this further. So let's say I have a positive ion which is very small. Positive ion and negative ion is very big. Okay, so something like this. So this one will not try to outrun this one. But the equation is telling me it cannot outrun. Great. So excellent answer. So what is the other mechanism? Is electromigration. So we eliminated phi, but that doesn't mean that electric field is not present in the system. So when it sees electric field sees, oh well, then positive ion is outrunning the negative ion, the electric field develops to retard the motion of the positive ion and accelerate the motion of the negative ion. So what happens is an electric field would develop like this, right? So that electric field will push the positive ion back because it's in this direction. Positive ion will respond to the electric field and it will pull the negative ion opposite to the electric field. And so they're both going to stick together and go together. So that's basically what's happening. That's the magic of electromigration, is that two ions with different diffusivities are still bound to behave together. Okay. This is what happens in bulk transport. Something what we will not discuss in the class, and something that Felipe discovered in his work, was that this all breaks when you have pores. In pores, we have surfaces now, and that surface is also interferes with this electric field. And his PhD thesis essentially has sort of shown us that you can actually break this. But in the bulk transport, when there are no surfaces, you can have the transport to them they have to stick together. But they do not have to stick together when they're under some confinement. And that's something we basically we have to, yes.
So instead of like stuck together, you just treat it as if it didn't dissociate, you just have like an NaCl neutral units that travel together.
Correct. So great question. So it's also a very nice question. So Tim is asking is whether they will always stick together. The answer is not necessarily. So why am I saying that? So you can have a calcium chloride and a magnesium chloride and a sodium chloride. Okay. Now I have chloride ions from all three of these, and sodium and magnesium, which is something we have not discussed here. So in that case, the chloride coming from sodium chloride will interact with the magnesium chloride. So it's kind of a mess in that case. So in a binary electrolyte, that is something how you can physically picture it. But as soon as I have multi-component, that all falls apart. So I would say that's not necessarily always the case. But right now, for a two-ion system, you can think of them, they are kind of moving as a couple. But it's not necessarily going to happen. Does that make sense physically? Any other questions here? All right, so let's take another question here, physical question, and that's the consider an electroneutral monovalent source. So monovalent means Z plus and Z minus are plus minus one. And so what do you think is the effective ambipolar diffusivity if dA is much greater than dB? Okay. You can use math or you can be physically you can motivate this answer. Both are correct, and we will discuss this. All right, maybe another 10 seconds to kind of close out this discussion. All right, so let's close this poll and let's look at the results. So the answer is still split, I would say, but the majority answer is D, which is actually the correct answer. It is 2 dB. So physically, let's look at it physically. Okay, so I don't know how many of you did it through math or physically. As you can imagine, if they're moving as a kind of collective trying to maintain electron neutrality, the diffusivity has to be between dA and dB. You have to kind of slow down on them. Let's say one of them. So dA and dB are not possible because it has to be slower and has to be faster. Okay? The faster one is dA. So I cannot have greater than dA. I can have greater than dB. So that's the way you can come out of D. So it has to be between. So basically, the other option, the way to think is the D is the only option between dA and dB. So that is one way to look at it. Or if you want to look at it mathematically, what I've done is this is a D effective. I've added +1 -1 as Z plus D minus. So you get 2D plus D minus, D plus D minus, or 2dA dB by dA plus dB. And if dA is greater than dB, then this will become approximately 2dA dB by dA goes away. So you get 2 dB. Okay, so you get 2 dB, and this is the mathematically answer. But remember that D effective has to be between D min, D max, and D min. Okay. D max and D min. Just remember that. And what kind of mean is this? 2d plus d plus by d minus d minus is the harmonic mean, right? So you have arithmetic mean, geometric mean, and harmonic mean. So if you write 1 by d plus, you can get to with the answer of harmonic mean. But this is only for z plus is equal to plus minus 1. So that's why we don't call that, because there is also z plus z minus and so on. So just so that you understand that. Okay. Any questions here? All right. So one last thing that we'll discuss before we end the class. So till now we have discussed, first we discussed electrolyte transport. We discussed this new term electromigration. We derived the Poisson-Nusselt equation, which are very difficult to solve. Then we said, well, we'll ignore velocity. We'll assume 1D system, right? And then we said, okay, 1D system, ignore velocity, and then bulk transport. So charge density is 0. We simplified the equation and they become basically diffusion equation. But the diffusivity constant is a combination of both the ions. And then if the diffusivity is a combination of both the ions, we derive that to be ambipolar diffusivity, which is always between the minimum and the maximum. Okay, so this is what we have discussed today. The one small thing I do want to mention, because some of you might be using this, is called how to calculate current. How to calculate current from transport, and it's something you may not have seen before, from fluxes. Okay, so what I'm saying is now how to calculate current. So let me just write current here. Current from fluxes. And current will be denoted by I. So please don't get confused with the I of the ith subscript. This is just the current I. You can call it J as well if you would like, but just to keep it simple, this is ZI NIF times area. Okay, ZI times NI times F, summation of I. Okay, and then this is, remember, this is unitless. This is mole per meter squared second. And this is coulomb per mole. So you get coulomb per meter squared second. And then there is an area which is meter square. So you get out to be coulomb per second, and coulomb per second is amperes, which is the current. Okay, so all you're doing is flux is the species transfer per unit area. You're multiplying that by the charge. That's all you're doing. And that's why you get current. Okay? And you can, all you need to do is you just need to plug the three combinations of this inside here. You will get Zi times Ci times velocity. This is very important. Minus Zi times Ci times Di grad, Di grad Ci. Di grad Ci. And Zi square Ci Di F by RT grad phi. Okay. So I just wanted to show this. So there are three parts: convection, diffusion, electromigration. Convection, diffusion, electromigration. And when rho E is equal to 0, what do you think will happen? What do you think will happen when rho is equal to 0? What happens with the first term? 0, right? Zi, so, and there is also an F, by the way. Sorry, I forgot to have an F everywhere. A square, okay? So Zi times C, so it will be 0, right? Zi Ci summation Zi Ci is 0. So this goes away. And this goes away. Because I can take that inside the gradient now. So all you are left with really is current is equal to area times minus Zi square Ci Di F square by RT summation grad phi. And does this remind you of something? Have you seen this somewhere? This is the Ohm's law, right? It is the Ohm's law. Yes. And did I miss something? Yeah. Yeah. Oh, sorry. I should mention. I forgot to mention that we assume that diffusivities are equal. Thanks, Philip. Yeah. So that's an assumption here. The diffusivities are equal D naught. So let's just before I forget. Thanks, Philippe. This is D naught. Okay. So that's why we can get the diffusive term out. Diffusivities are equal, and then so you get this term, and this is the Ohm's law, right? This is the Ohm's law. Ohm's law, and this portion is the conductivity of an electrolyte. Conductivity of an electrolyte. So when you have the bulk transport, and I should have mentioned this, bulk transport is equal diffusivity of the ion. Then if you apply an electric field, measure a current, you can get out the conductivity of the electrolyte. And conductivity of the electrolyte is a very important portion because it tells you how much you will lose in terms of, potential drop across an electrolyte. So this is a very common experimental technique to characterize, and some of you may be actually using this to characterize some of your electrolytes if you work with them in the lab. Okay. So essentially, Poisson-Planck equation can give you an Ohm's law. All right, so that's it for today's lecture. Just one personal appeal is to please fill out the FCQs. It's very important. Last 2 times we have taught this course.